First is LiDAR failure, where the probability of failure is 10%. This information, gathered from another source, was done with the simulation experiment. It was then analyzed using the Bayesian belief network. Some characteristics of failure include laser malfunction, mirror motor malfunction, position encoder failure, overvoltage, short circuit, and optical receiver damages. Next is radar failure, where the probability of failure is 2%. This number was found from another source, which used mathematical modeling to gather results. These results were analyzed using chi-square distribution, and those failures can be seen in detection curves drawn with respect to signal and noise damages. Next is camera failure, where the probability of failure is 4.95%. This information, gathered from another source, was done with a simulation experiment. It was then analyzed with the Bayesian belief network. Some characteristics of failure include foreign particles, shock waves, overvoltage, short circuits, and vibration from rough terrain. Next is wheel encoder failure, where the probability of failure is 4%. This number was found from another source, which used an original experiment. The data was then analyzed using the Kalman filter. Failure was found when encoder feedback was unable to be transferred, in addition to the loss of synchronization of motor, stator, and rotor positions. Next is GPS failure, where the probability of failure is 0.925%. We got this number from another source, which used experiments from 4 different locations. The data was analyzed using the least squares method, and the tests were performed with high-sensitive GPS in different signal environments for more than 14 hours. Next is integrated platform failure, where the probability of failure is 2%. This number was found from another source, which used mathematical modeling to gather results. These results were analyzed using the Markov chain model. The failure can be seen in 2-state models with failure rates that were developed to estimate the computer system availability. Next is software failure, where the probability of failure is 1%. This information, gathered from another source, was found with an original experiment with 3,000 runs. It was then analyzed using the Markov and Bayesian network methods. The failure can be seen when the system had to generate outputs from array definition language statements. Next is database service failure, where the probability of failure is 3.86%. This number, gathered from another source, was found with an original experiment that lasted 191 days. The data was analyzed using the Generic Quorum System Evaluator, or GQE. This new empirical approach collected connectivity and operability data, which is where the failure was found. Next is communication failure, where the probability of failure is 5.125%. This information, gathered from a different source, was found with an experiment using 10 vehicles. This data was analyzed with the IEEE 802.11b network method. The series of experiments were done by sending 10 1,000 byte frames periodically and recorded whether received or not. Next type of failure is when the system failed to detect human command, where the probability of failure is 1.4%. This data was found by another source, which used experiments with 37 subjects and 185 recordings. The data was then analyzed using artificial neural networks on clean speech. In some experiments, the system was unable to detect the accurate acoustic command. The driver would input the wrong command, and the system was unable to detect that wrong command. Non-autonomous vehicle crashes have been found to have a failure probability of 1.299% by other researchers. Reasons for failure are crashes due to reckless driving, tiredness, hardware, and distractions.
Weather-related incidents. With poor conditions such as fog, mist, rain, severe crosswinds, sleet, snow, dust, and smoke, we found a probability of failure of 0.218%. Road conditions are related to the improper lane markings and pavement conditions such as shown in the picture below. With this and our studies, we found that a failure probability of 6.39 times 10 to the negative third percent. Cyclists. Among the 9 million bike trips made daily, the NHTSA in 2014 recorded that cyclist accidents with vehicles caused 726 deaths and 50,000 injuries. 16.5% of the time, cyclists were at fault. Based on this information, the failure probability of 9.4 times 10 to the negative fifth power was found. Pedestrians. Among the 42 billion walking trips made annually, 51% of these crashes were pedestrians' fault. Based on this, 2.05 times 10 to the negative fifth power failure probability was found. Construction zones. Among all work zones, 41.33% were rear-end crashes. This tended to cause a failure probability of 7.42 times 10 to the negative fourth percent. This project was funded by the UTRC Region 2, and on behalf of the Rowan University and Clemson University team, we would like to thank you for watching this video.